Okay. First, let me share my screen. As the instruction in the Moodle, we should go to the GitHub and download the release version of the code here, and you should download this one. This one is the stable one. You should use this one, and I download here, and you can see I download here, and unzip it. This one. And you can also download this file fluid 2D channel flow, and also unzip it. And then copy this whole folder to the case user file. And then we should use CMake to open this SPHinXsys project, and we should rebuild a new folder. Means SPHinXsys build. And we open a CMake to here below source, and we relocate the source file right here. Source file here, and download from the GitHub, and including our first cases. And here building should choose the one we just create here. And then configure it. Choose x64. And then generate. Open project. Now we can see here, we have the cases here, biofluid 2D channel flow. We can right click here and set as startup project, and open this CP file. Okay. And then we come to the project here. Then I will instruct this code line by line. So first we come to this line, include the SPHinXsys.h, and this line gets us all the declarations we need. And then we come to the using namespace SPH. This one includes nearly all the symbols used by SPHinXsys. And then we come to the bicycle geometry parameters. And we can show here. This one is the cases we will get today. And you can see here the coordinates is here, and we have the DL sponge, DL inlet, and the DL outlet, and the channel flow, the height we named the DH. And in this case, we have two branches, upper branch and under branch. They have different width. And the green one is the wall boundary. We name the BW. Okay, and the values for these parameters we give here. And for this one, for N, because we have to correct in the semicircle, so and the semicircle is created by multiple points, so we give 180 points for each semicircle. And this one is resolution ref, means the particle spacing, and the DL sponge. DL sponge, sponge area. We use the sponge area to make the inflow more stable. You can see here, sponge area at the beginning of the inflow. And we comes to bounding box. Bounding box. Bounding box gives the coordinates of lower and upper bounds of the domain, and which will be used as the bounds for mesh used for cell linked list. Now, and then we give the material properties. Density here, because in SPHinXsys we are using a weakly compressible.
Dong, I think you can close the output setting, so then you can show more source of the code.
Output.
Yeah, the output, the Visual Studio. You can close the output.
Close the output.
Yeah. I mean, in Visual Studio, you can close the output section and show more of the code.
You mean?
No. Lawyer.
You mean here output?
No. I mean, 你可以把那个输出栏关掉，你这样你能够看到。
You mean this one output?
Yeah.
Okay. And here we use the characteristic velocity and the speed of sound, because we are using the weakly compressible model for imposing compressibility. So the maximum speed and the sound speed in the flow and the sound speed are estimated. And we give the real number and dynamic velocity. Then we comes to the geometry we need for this case. We first create the water block. I can show you here how to create the water block. And first we create, you can see here, this one is the water break, and first we create a rectangle. And here also show the size. And after this, we create a semicircle and the upper semicircle. And then we create another semicircle. Here I want to say now is the problem with creating bodies net overlap. And after this, we should subtract a circle in the middle, and in this way we get the water block. And you can go back we can go back to the code. Here first, we create the rectangle. We give 4 points, and at the last line, this line is the same is this line. So we should close the shape, and then we create what block shape 2, the semicircle, up semicircle, shape 3, the under semicircle. And after this, we jump to create the water block. What I said just is to create the shape, and this one is to create the water block. You can see here, we use the class we defined before, and we create shape 1, shape 2, shape 3, and we use this command, add a polygon, to add shape 1, shape 2, and shape 3, and we use add command to subtract a circle in the middle. So in this way, we create the water block, and the wall boundary and the observer body is almost same with creating water block. But I want to show, but we should notice that it's better to make the solid part smoother. We call this function as relaxation. And in order to relaxation, you see here we call the wall boundary. In order to relax the wall boundary, we should use this class. Before it's same with the water block, and we should use this class to define the boundary shape. And this one I said is well used for the relaxation. And we in the middle, we also define the water material and inflow buffer. Inflow buffer means the sponge area. And here we comes to the inflow boundary condition. For the inflow boundary condition, we show you here. For the sponge area, you can see here. You can see before sponge area is the position x is smaller than 0. So if x is smaller than 0, we give the velocity here. This is the velocity in x direction, in the y direction. So this is the equation, and your average is equal to here. Your average is the function of sine function. Is the sine function. Here we also give the parameters. For this equation, we give the inflow boundary parabolic distribution. You can see here. So you can see here we give the parameter values, and here we get the U average, and here we give the velocity. Observer, define observer. Observer body, we give 21 observer points, and you can see here we push back using a for loop to push back the observer points positions. This one we we can show you here. We just create the free observer points at the inflow, and we comes to the main function. Before the main function, we define the geometry parameters, define geometries, and we comes to the main function. Here we here an system object of the SPH system is created here. This one system bounds we defined before, and the resolution ref, and then we also define a global physical time initialized, and the whether the computation begin from a restart file is checked here. And I want to instruct this two line. Here we also have a comment. If you want to use the relaxation, you should run the code twice. First time you should run this case and change this one to true and this one to false. And if you run this case, they will run with the relaxation function, but the fluid dynamics will not be included. We can do the first, for this time, for the first time to run this code, we will get the results with relaxation, and I can show you the relaxation with relaxation and without relaxation. I think I have need problems with my computer. Because I am compiling my code, so it's need hard for my computer to show something. Please wait a minute. And now I'm showing the results with relaxation and without relaxation. You can see for the relaxation, we can get the smooth boundary condition or boundary shape. And for the without relaxation, looks bad. Yeah. And we come back to the code. And then we the water block, the water material, and the water particles are created, and then it's same for the water boundary and the fluid observer. But for for the wall boundary and observer, we don't need to define the materials. And then data file input and output functions are defined. Including read restart file, write restart file. And then we come to the topology. And here we define topological relations, which specify each body the possible interacting bodies. You can see here the water block will be interacted by the wall boundary, and the fluid observer will be interacted by the water block. And here we will check whether run the particle relaxation. You can see here we define this one before. You can see here. If we choose this true, we will run this part. This one is the relaxation. If we do not run it, we don't want to run the relaxation, we choose false, and we can jump to. We can come back to this later, and we just go to next slide. And then we come to the to the method for the time stepping. And these lines will these objects defined will use the multi times in a loop, and we including calculate time step and update density, and this one is for fluid dynamics, and the velocity correction, and we compute vorticity, and we get the parabolic inflow boundary condition. Here we define how to write the fluid velocity, and define to write the observer quantities. And then we come to operate simulation. First, we will check whether to reload to using the relaxed particles. You can see we also defined before. If it's true, we will use the relaxation particles. And then when it comes to initialize simulate system cell link list, and the initialize system configuration, and for the initialize the normal direction. For the initial system configuration, we need this function is to find the label particles for each particle, and then we comes to the time stepping. Here we will ask whether the restart step is equal to 0, because because this code will write the restart file as we said before, and if you can see, we define the restart step before it's equal to 0. If it's equal to 0, we will jump this code. It's not equal to 0. Because our code will output the restart file every time. If your code crashed, for some reason crashed, you can set the restart step, and then you can run the code start from the restart times. From the restart time, and this one is to output the real body status. It's first output, and we didn't run a fluid dynamic, so everything is 0 for velocity is 0, something like that. And here we give the basic control parameters for the simulation, such as the restart, such as the restart step, output frequency, the total simulation time, and the interval for writing output files. And the time step sizes are initialized right here. Here we comes to the time stepping loop, the main loop. The computation is carried out with a dual criteria time stepping scheme. As discussed in the PDF file and the PDF documentation of SPHinXsys, you can download it from the Moodle. And during the looping outputs are scheduled, on screen output will be the number of time steps, the current physical time, the adventure time step size, and this one means how many acoustic time steps are there in advection time step size. After the simulation is terminated, the statistics of computation time are output to the screen. And now let the total computation time has excluded the time for writing files. We can go to details later, but now we can try to run this code. As I said, if you want to run relaxation, we should change this one to true. And this one is false for the first time. We can have a wrong. Okay, let's think like now. Oh no. And after the simulation, we will get the output files. For output files, because the comparing step should spend some time, so I try to explain something here. Okay. No. Here, the output file is in the VTU file. The VTU files can be read directly by the open source visualization called ParaView. And you can also have the option to save the files in TechBlock format. You can change VTU, just change VTU to PLT. It's okay. Now you will get the PLT file and can be read by the TechBlock. And we change back. I think we almost finished the compile. Okay, and now we start the relaxation function, and the screen will show the physical relaxation process of the cylinder finish. Okay, no, not the cylinder. It should be our boundary, and we can go to the user file and user find our file and go to SRC file, SRC folder, and we can see here we get 3 photos for the first time simulation, and we restart because we actually didn't run the simulation, so we didn't have the restart file. And we can see here reload file. Reload file is for the relaxation, and we can change here for the second time. We should change here to false, change here to true, and if here is true, we will read this file. This file is for the boundary relaxation particles, and the output is also the relaxation particles. Actually, we can read this file by the ParaView. We can open the ParaView. Open ParaView. Desktop. Post. Build. User. SRC output. We can read this one and this one. One is for wall boundary, one is for water body. Okay, and apply. For wall, we should change here to point Gaussian. This one is same. And filter screen. Okay, you can see here we get the particles, but it's too large. We can change here radius to be smaller. Okay, and the fluid body is same. Okay. Okay. You can see here we output the wall boundary. It's six files, and you can. It's the first output file. It looks like here. I close it here, and then it will be better and better. So now we get this shape, these particle distributions, and output this particle distribution into the reload folder here. So and then we run the second time. Second time we here should be false, here should be true, and we run second time. Just here is okay. And you can see here the output screen will show the let me have a look. Will show the number of time steps here and the total time, and the dt is the add vacuum time step size, and the dt that was dt it's the how many acoustic time steps are there in at the vacuum time step size. So it's the output screen, and you can show here total wall time for computation is 20 seconds. And then in this way we finish the second time simulation, and we can open the output file. You can see here output file now it looks like this. Just one file for wall, because we actually didn't update the wall conditions, because it's the same as the whole simulation, and we output the water block status by time. And we go back to parallel view. We open these two. You can see we choose this one. It's choose the water body output files. And okay, and we close this one and apply. Just the same as before. We change here. Here and reduce the radius, and we can show the here show the velocity, and I'll go to the first output file, and the velocity here is equal to 0, and at the first time at the beginning, and we can this command is to rescale the velocity from beginning. So here's what we get. It's the velocity looks like because the inflow, the velocity of the inflow is the function of sine function. I showed before. It looks like this. So, so the velocity will change with time. So it should look like the velocity change with time, and the results should look like this one. So I almost finished the code, but we can have some more practice. For example, we can change the size. For example, we can change the branch size. We change here to smaller one, and here to big one. We can run again, but remember to change here. First time we should change like this and run again. Okay, it's output. Okay, we finish the relaxation and we change back. Okay, change back. Okay, run again. And do you have any questions? And we reload the file. You can just right click here and choose to reload the file and choose find a new file. This one is same, but I think this one cannot. Yeah, it cannot. For the wall boundary, we should open again, but no, I just didn't open the wall boundary. And you can see here it's the branch size. We change the branch size and the results look like this. And we can show here. Okay, and except change the size, we can also change the resolution. We can run again with the high resolution. With high resolution, we should change here. This one is the particle spacing. If we change it to 0.1, change it to 0.05. Okay. And the same we should change here, but the high resolution should spend many time to run. So I just get the results before, and I can show you directly. It's the high resolution results, and I can show you this one. Okay. We can make this bigger. For the wall boundary, we just have because just have 4 layers of wall boundary, because we defined at the beginning, at the code of the code, we define the wall boundary size, wall boundary thickness is equal to the 4 times of the particle spacing. So we just get the 4 layers where no matter the resolution. So and if you like, you can also change it. I change the high resolution back to low resolution. It's better to show the case. It's better to show the case, and then we can, if you like, you can also change the inflow velocity. Change here. Inflow velocity I showed here. We define uref is equal to 1, and U average is related to uref, and the velocity is related to the U average. So we just change the uref. So you can try. I change to 2, and we should again. Oh no. Okay. Change back. Okay, I reload the file. Okay, it's the result look like this. So do you have any questions? And do anyone run this case and before this class? Okay, I have a chat.
So anyone have any question concerning the code or this example? So if